So now we've talked through all the different fields that are really important for understanding TCP and how it provides the functionality it provides. We've learned enough that we can really start to begin to understand normal stimulus and response. And hopefully through some of the things we've already talked about in the packets we've already examined, you've kind of picked up on some of those things. But if not, don't worry. We're going to go through some of the basic stimulus and response here. Again, both normal and abnormal. We're going to start with the TCP handshake, and the simple reason for this is because it's how every TCP conversation begins. If TCP is going to have all these great error recovery and flow control mechanisms, it has to have the concept of a session. Right? So when you have a session, that means you have communication that both hosts are aware of. That means they're aware that the session exists as a construct, and they're aware of the components of that session such that they can monitor them, monitor their health and their state, and that's what allows for things like flow control and retransmissions and all those things that make TCP the reliable protocol it is. So in order to have a session, you have to set up the session, and that involves a few steps, and that's the process known as the TCP handshake or the TCP three-way handshake, because it is indeed three individual steps. Now, in this process, we generally have two systems. We're unicasting here, so we have System A talking to System B, and we have System A who wants to initiate the connection to System B. And to do that, it's going to send a TCP control packet with the SYN flag set and only the SYN flag set. So that's going to be the primary thing that identifies this as a session initiation packet. Now, what this is also going to include some of the information we've already talked about, things like an initial sequence number, things like supported TCP options. The purpose isn't only to say, hey, I'm here and I want to talk. It's also to say, here, hey, I'm here, I want to talk. This is how I want to talk, and here are the features I support, and here's some information you can use to talk to me. Right? Of course, things like source port number are also important for that, because System B needs a port to talk back to System A on. So the initial SYN sends all of that data back. Now, when System B receives this packet, it's going to take it, and if it's listening on the port that's being communicated on, it's going to respond back with a packet whose SYN and ACK flags are set. So in this case, it's sending the ACK because it's going to acknowledge the initial SYN that was sent. It's going to increment the sequence number it got by 1, send that back, so System A will know what the next sequence number needs to be. And it will also send its own SYN it's got the SYN flag set itself, so it's sending the same information that System A sent, but it's sending it in this packet, right? So it's sending its own initial sequence number, its own supported options, and it's through mutual support of specific options that they can be enabled. Some options do require support on both ends in order for those to be able to be used during communication. Once System A receives the SYN-ACK packet back, it's simply going to respond with an acknowledgement packet, so a packet with the ACK flag set, and that is going to fully establish the session. Really, all the hard work's being done in the first two packets. That's where you're communicating the options and initial sequence numbers. The final ACK is just System A acknowledging System B's SYN information. It's got to acknowledge that communication. So this is the standard TCP three-way handshake. Generally speaking, anytime you see a new TCP conversation begin, you're going to see one of these handshakes. At some point, as you get really experienced looking at packets, going through Wireshark, going through TCP dump or T-Shark, you'll learn to very quickly spot this SYN, SYN-ACK, ACK trio of packets to identify new conversations. I can be looking at a list now of like 50 packets from halfway across the room, and I can say, oh, there's two conversations that are starting here because I can recognize this SYN, SYN-ACK, ACK that's going on. So that's an important way to recognize that conversation exists and is going on. You're looking at a file now called tcp_handshake.pcapng, and it's exactly that. It's just a simple TCP handshake that begins a TCP conversation. In this case, we have a conversation being initiated from 172.16.16.128 destined to 212.58.226.142. It looks like we have a random source port chosen, and we're going to port 80. So we're communicating in this case with a web server. And to do that, we have to set up this initial TCP session, transfer the data we talked about in terms of supported options, initial sequence numbers, and then the communication begin. And that's what we have going on here. So I'm going to click into this first packet here. and expand the TCP header and scroll down. And what I want to show you first are the flags setting. So I have flags here, and it's collapsed, and it just tells me that the value is such that the SYN flag is set, and that's the only thing. I can actually expand that here, and it'll show me here that all these are a value of 0 except for the SYN bit, which is set to 1, which is what we're going to use here to define the fact that this is establishing a new connection. So pretty straightforward. The information we need to transmit is also going to be here as well. So we see sequence number. In this case, the sequence number is 0 because Wireshark relative sequence numbers are enabled for the TCP analyzer. If that was disabled, we'd get the actual sequence number. But for us, just knowing that it's here is fine. Of course, if we look down at the bytes, we can see what that is in hex. So that information is available in that way as well. Beyond that, we have TCP options that are supported. If I expand this, we see we have maximum segment size, window scale, and TCP selective acknowledgement that are all permitted here. So those are being transmitted to the recipient, who can then send its own list of supported options, and the mutual agreement of what and how the communication should work will then be completed at that point. We'll see that here in the second packet. And if you look over here in the packet list pane under info, we see that the flags for TCP packets when they're TCP control packets is listed here in the info column. So here we saw that there was a SYN. Here we see we have SYN and ACK both set. And then in the third packet, we'll have an ACK set. But for this one, we have both SYN and ACK. If we go down to the flags section of the TCP header, we see that there's a 1 in the SYN position, 1 in the ACK position, and in this case, both of those flags are set. Again, a single TCP packet isn't required to only have one flag set. It can have multiple flags set. In this case, SYN and ACK are both set. We have more options here. In this case, we have the recipient sending its maximum segment size, which looks like it's a little bit different. It also allows for TCP SAC, and it also provides a window scale value, albeit a different one from the one offered by the initiating host. Of course, it's going to provide its own sequence number here, as well as an acknowledgement number to the initial sequence number it received in the initial SYN packet. And so at this point, once these two packets are received, the hosts both have what they need for the most part to communicate. There is one final packet, which is an acknowledgement packet. We see the acknowledgement bit set here. That's sent to provide to continue the TCP communication so that the other host knows what acknowledgement or what sequence number it should use next. But once all these three packets have been transmitted, communicated, and received, normal communication can begin. So in this case, this is HTTP traffic. So if there were a fourth packet here, you would see that it would probably be an HTTP GET request for a specific web page, right? So pretty straightforward three-way handshake process, SYN, SYN-ACK, ACK. You're going to see that to start every TCP communication sequence you see, assuming you're capturing the packet stream before it's actually begun. If you capture the packet stream in the middle of the communication sequence, you're probably going to miss this. But if you start from the beginning, you should always see this SYN, SYN-ACK, ACK sequence that goes on as part of the TCP three-way handshake. Now, since TCP went to all this work to set up a formal session with the TCP handshake process, you might expect that it also has a complementary function to formally terminate the connection. And you'd be right, it does, and that's called the TCP teardown process, which we want to talk about here. Now, whereas the TCP handshake is a three-step process, this is actually a four-step process, but it's still pretty simple and pretty straightforward. In this case, we have System A who's communicating with System B, and at some point the communication is over. System A doesn't have any more data to send to System B, so it's going to send a TCP control packet with the FIN and ACK flags set. Once System B receives this, it's going to reply with an acknowledgement packet, as is the way of TCP, and then it's going to send its own FIN-ACK TCP control packet back to System A. So what we actually have here is we're closing the connection from both sides. That's the best way to think about this. So while this is a four-step process, you really have essentially two-step processes going on. Once System A receives System B's FIN-ACK, it's going to respond with its own ACK packet, and then the communication is over. It's terminated. You shouldn't see any more packets. TCP packets is part of this stream between these hosts without the setup of a new connection. So if System B decides it needs something else from System A, it at this point would need to initiate a new TCP handshake sequence with new sequence numbers and all of that stuff. But this is, again, a pretty straightforward process, 4 steps, FIN-ACK, ACK, FIN-ACK, ACK. Here's a packet capture demonstrating the TCP teardown sequence, and we'll make quick work of this one because it's pretty straightforward. For the most part, they're just basic TCP control packets with the appropriate flags set. In this case, we begin where 67.228.110.120 is sending a packet to 172.16.16.128 to initiate the end of a conversation. In this case, it's being sent, it looks like, from a web server to a web client because there's no more information to deliver. See, the fin and ACK bits are set here. We see that in the info column as well as down here in the packet details area. Fin and ACK are set. The client, in this case, the 172 address, responds with a simple ACK. At that point, the client also then sends its own fin ACK to initiate the closure of the connection from its side, wherein the server then responds with its own ACK. So we have this four-step process: fin ACK ACK, fin ACK ACK, and that gracefully tears down this TCP communication sequence between a web client and a web server who are using TCP, which is used as a part of, which is relied upon by HTTP. In an ideal world, most of our connections end with a graceful termination using the FIN-ACK sequence we just talked about. But unfortunately, not all worlds are ideal, and sometimes connections have to end a bit more abruptly. I spoke about this earlier when I said a normal TCP teardown using the FIN flag is more like saying, okay, you have a nice day, goodbye, and gracefully ending a call. A TCP reset is more like just hanging up on someone, and in many cases, TCP does just need to hang up on someone. So there are a couple of different scenarios at play here. In this case, consider we have System A talking to System B, and System A sends a send packet to System B to set up a new connection. However, in this case, System B is not accepting new connections. Could be for a number of reasons. Maybe this individual port is closed. Maybe there's a firewall in place that's blocking something. Could be a number of things. In this case, System B is going to let System A know that by sending a reset packet back. And this is actually a flag with both the reset and ACK flags set to 1. So reset ACK, it's going to send that to it, and System A will not attempt to send any more packets to System B on that port, or at least it won't automatically do that as a function of TCP. Now, there might be some application layer protocol that wants to retry the connection and that will have it initiate a new send packet to try to do this again, but this specific TCP connection will be dead at that point. And no communication will be allowed to continue because System B isn't willing to accept it. So it's almost like calling someone and saying hello, and they just hang up on you immediately, except in this case, System B isn't actually saying anything back. It's just the immediate termination of the connection. Now, resets don't have to occur upon an initial connection. So we may have a scenario where System A is already communicating with System B. System B sent some data to System A, and then all of a sudden something weird happens on System B. And this can be any number of things. Service crashes, the system locks up, there's some type of administrative action going on, and System B can then immediately send a reset packet. And this can sometimes be just with the reset flag set. Sometimes it can be a reset ACK packet. It's going to vary a little bit based upon the situation. But resets are a normal part of stimulus and response for TCP. You might look at these things and say, well, isn't this abnormal? And it can be abnormal depending upon what you're expecting, but resets are normal functionality of the protocol itself and are expected in these cases. Like the first case, if you send a SYN to a system which has a closed port that it's not listening on, getting a reset ACK back is perfectly normal. I'll show you an example of a TCP connection being refused in a reset packet. But in this case, we've been doing a lot of Wireshark. I want to show you what this looks like in T-Shark, which is honestly not going to be too very different. But if I open the file TCP refuse connection .pcap, we'll see two packets here. We see one, the first packet is from 192.168.100.138 going to the host 192.168.100.1. It's a TCP packet. It looks like it's going to port 80, and it looks like it's a SYN. So it's establishing a new TCP connection, or at least attempting to. The second packet, however, comes back from 192.168.100.1. And in this case, we see reset ACK. So apparently this host isn't listening on this port, so it sends reset ACK back, and there is no further communication. The communication is now dead. So pretty straightforward. We can gather all that information just by looking at these flags here. They tell us the sequence of the communication because after all, the flags do tell us the purpose of these TCP control packets. So pretty straightforward process, TCP resets. Now, of course, when you see a TCP reset in your troubleshooting, chances are you might be troubleshooting the issue that's getting reset. So at least this will help you determine the source of the issue. In this case, if you're troubleshooting, you would say, okay, well, 192.168.100.138 sent the initial connection request. It did initiate the connection, but it was not received. It was blocked for some reason by 192.168.100.1. So that's probably where your troubleshooting needs to be focused. So packet analysis doesn't always tell us the answer, but it often does tell us where we need to look. And this is a good example of a case where we now know where we need to look. So when talking about normal stimulus and response for TCP-based connections, you run into a lot of different scenarios. We talked about already a normal connection scenario where we have a handshake, a send, send, ACK. We've talked about refused connections, but there's quite a few more scenarios that come into play. So I kind of want to hit on a couple of those now and some of the things you might expect to see. Let's say in this example, we have a device, a web client that wants to send a send packet to a web server on port 80. It wants to download something from what it believes is a web server. So what would be the expected response back from this stimulus in a number of different scenarios? Well, if the host is up and listening on port 80 and everything's honky-dory, we should get a send ACK back. And then we're going to send an ACK and complete the three-way handshake, and we can go ahead and request data with HTTP. Well, if the host is not listening on port 80, well, that's the scenario we just talked about with a TCP refused connection, wherein we'd probably get a reset ACK back because that port is closed. What about if the host is down altogether? In this case, you might see an ICMP type 3 code 1, which is a destination host unreachable message. So ICMP is actually coming in to help here because the host isn't up to respond. The host can't send a reset ACK because it doesn't exist or it's completely down. So ICMP might step in there. Now, what if the host is blocked or the connection is blocked by a router or firewall, either a host-based one or something network-based? Well, there's a couple of things that could happen here. One is that we could just get no response at all. Whatever the recipient device is may be configured not to send resets or ACKs or anything specific. We might also receive an ICMP type 3 code 10 message, which means admin prohibited to host. We might also even see a reset of some sort or a reset ACK. And I say that there are different options here because different operating systems handle this different ways. And when you think about operating systems, we don't have to contend with just Windows or Linux or Mac. We also have the operating systems running on intermediate routers between us and our destination host. So those are all things to consider. There are a lot of different scenarios that come into play with normal stimulus and response for these different TCP connections in the end state. So these are all things to keep in mind. These are the most common things you'll see. However, that said, the most important thing to remember is that TCP is based upon an RFC specification, and that RFC specification is pretty detailed, but it's not ultimately detailed. It doesn't cover every single scenario that you're going to see. Therefore, operating system manufacturers and those who develop TCP stacks, TCP/IP stacks, they can implement certain features certain ways, and even some of them, even things that are well documented, they tweak those a little bit for the sake of efficiency or performance or something like that. So your mileage may vary with normal stimulus and response in this regard. For the most part, these first couple of things, whether the host is up and listening or not listening, things like that, or the host is down, those are generally going to be followed. But when you get into the sense where something's being blocked by a router or firewall, your responses may vary a little bit, and you may see a little variance in what you would expect there. When you see that variance, that would certainly fall into the bucket of abnormal stimulus and response. What I have listed on this page here is what I would consider normal, and many of the things outside of this would be considered abnormal. But just because they're abnormal doesn't mean they're not perfectly healthy or perfectly okay. They're just not what you would normally expect to see. Nonetheless, if you can remember the things on this list, you'll be well on your way to kind of understanding most of the typical stimulus and response related to establishing TCP connections. Now we'll move on to abnormal stimulus and response, and we'll talk about a couple different scenarios here. As I mentioned, TCP/IP stacks can be implemented in a few different ways, and the TCP spec isn't all-encompassing. So you see a little bit of weirdness in a lot of places, and it's impossible for us to cover all that. Hopefully by covering normal stimulus and response and all those connection scenarios the way we did, that prepares you for what kind of can be bucketized as normal and what can be bucketized as abnormal. But I still want to cover a few specific abnormal SNR scenarios, and we'll do that by starting first with half-open connections. In a half-open connection, we have two systems that are communicating, System A and System B. And in this case, System A sends a SYN packet to initiate a new connection to System B. System B responds with a SYN ACK and waits for an ACK. But you know what? It never gets one. System A never fully completes the connection, and the connection is left sitting in a half-open state. And you might ask, well, why would System A do that? Why wouldn't it want to complete this so it can communicate? And generally the reason is because System A never actually intended to communicate with System B in the first place, right? And there's a couple reasons for this. One of the most common is port scanning. So if it just wants to see if System B is up and it's listening and accepting connections on a specific port, then it can send that SYN, wait for the response back, and if it gets it, it knows that port's open, and the person on the other end, whether that's an automated process or a human attacker, they can begin probing that service later on. So you'll see this technique used with a lot of port scanners. Also, you have this concept of a TCP connection buffer where you don't see this as much now, but back quite a while ago, systems had a very limited number of TCP connections they could store in their system buffer. And when you sent a SYN packet, got the SYN back but never completed the handshake, those entries would remain persistent in that cache and they wouldn't purge out of there for quite some time. So the idea is if you could send enough of those half-open connections to a host, you can actually create a denial of service condition where it can no longer accept new connections. So essentially denial of service type attack via half-open connections. So those are a couple scenarios when you see that. 99% of the time you see it, it's generally going to be scanning. You don't really see that type of TCP connection buffer exhaustion anymore on modern systems. So when I see this, I usually think scanning. The next scenario I want to discuss relates to spoofed sources of TCP packets. Now in this case we have System A and System B, and no, your head is not turned sideways. They are staggered a little bit, and there's a reason for that, so bear with me. In this case, System A has an IP address 192.168.0.22. System B has an IP address 192.168.0.33. System A sends a packet to set up a new connection with System B, and it sends it with the information you see on the screen here. Now you notice the destination IP is what you would expect. It's 192.168.0.33, the IP address assigned to System B. However, look at that source IP address, 192.168.0.199. Well, that's not System A. That's not System A at all. So what's going to happen when System A sends this to System B? Well, System B is going to take it and it's going to respond to it. But when it responds, it's actually going to send the data back to System C, which is 192.168.0.199. It's the system that owns that IP address that was in the source address field. Now, in this case, System C is going to see that packet. It's going to get that ACK packet back, and it's going to drop it. It's not going to respond to it, or maybe it responds to it with a reset or an ACK or reset ACK, something like that, depending upon the OS version. But it's not going to accept that, and it's not going to complete the connection because it didn't send that initial SYN packet. The operating system isn't going to know what to do with it. It doesn't have a port bound and listening for that information. So this is kind of one of those relics of TCP, such that the recipient system, in this case System B, will process the information as it's received. But since the session hasn't been properly set up, System C is not going to complete that. So again, you would ask the question, why would System A do this? Why would it try to spoof this source address? And there are a couple reasons for that. As far as spoofing the address in order to hijack communication, that's not the easiest thing. There are some very obscure ways you can guess initial sequence numbers and do some things like that, but most of them don't really work too well in practice. We're not going to cover them here. But another thought might be a denial of service type attack, or just to mess with someone, mess with the defender, confuse some things with some packet wizardry there. So there are a few different reasons for that. Denial of service, again, being one of the most thought of, because this allows System A to send data to System B and then essentially have System B send those packets to System C. And if you do this at such a really high scale, you could denial of service System C, and that system would not know that System A was responsible. So it kind of passes the buck. In this regard, System C never sees traffic from System A. It only sees it from B, and then that's kind of hidden in that regard. So this is just an example of how very simple spoofing can occur, not to a very specific end, but spoofing nonetheless.